Hey everybody, my name is Bryce Frank. I'm a forest biometrician practicing in the Pacific Northwest, and you're watching a video about contributing models to the allometric R package that is storing and allowing people to use and easily access allometric models used in forest inventories and carbon inventories and things like this. So the subject of this video is to cover it's sort of an entry point into contributing models to the package. If you're interested in doing that, you're going to need to know a lot about these two classes called FixedEffectsSet and FixedEffectsModel. So the approach of this video is that I'm just going to take two publications and show you what I did, right? How I wrote them up and converted them into these classes. And that should give you some kind of grounding example. We'll fix that. Sorry about that. It should give you some kind of grounding into how to use these classes alongside a publication that maybe you're interested in adding, right? So this does take a lot of work and a lot of practice. There is an art to it. It's not an exact science, and that's okay, right? So if you have the wherewithal to go ahead and try this, I encourage you to just go try, right? And just send me whatever you come up with, because I'm happy to fix it, and it won't take me that much time because I've been doing this a lot. So please don't be shy, be brave. Feel free to email me, and you can contact me at this email address here, right? So it would be a great, actually in this first publication, we'll find a good low-hanging fruit for somebody to try and tackle. So maybe eventually we'll see something come out of this video, and maybe we could add another video showing what the person did and so on. So anyway, yeah, go ahead and contact me here if you ever want to take a stab or need a little bit of help getting started. So the fixed effects set is the one that we're going to start with, and the reason we start with this one is because it's the most commonly used class to use to establish allometric models in the package. I would say probably 80% of the papers have a fixed effects set. And we're going to take a look at Temesgen et al. 2007, which is a paper that involves height diameter models. So I have a diameter and I need to know the tree's height. This is one of the most common allometric relationships that we look at. So after that, we'll proceed to the fixed effects model. And this is the second most common thing that you'll use, the class that you'll use in the package. And this applies to the case where I only need to add a single model at a time to the package, whereas fixed effects set involves adding basically kind of like tables of models, you can think of them as. So we're going to take a look at Harrington and Curtis 1986, which is a site index paper for red alder. And I apologize, there is no italics in Notepad, so you'll have to forgive me there. But yeah, let's go ahead and get started. Okay, so one thing we're going to do in this video is just kind of walk you through how you might create one of these R files, one of these publication files. In this case, we're looking at Temesgen 2007.r, and it's already been written, right? So we're just going to kind of go over like how you would approach doing this. On the right-hand side, you have the publication itself, which is freely available on the internet, this PDF. So, the first thing to point out, of course, is that when we're creating the citation for the paper, it should match what you see here on the right-hand side as best as possible. So I'm not going to get into the nitty-gritty of like how to find this information, but there's pretty easy ways to do it. We're going to focus mostly on like how to find the models in the paper and add them today. So one other thing to point out is that a publication can get a list of what are called descriptors, which are just kind of like metadata about the models, right? And the standard, kind of the most standard ones you'll see are the country, which can be a vector or just one value. In this case, it's the US. So, you can see from the paper that we're in Southwest Oregon, which is a state in the US. So obviously the model should apply to the US. And the region is US-OR, which applies to Oregon, right? So we could say something about Southwest or something like that. I tend to kind of be a little bit hands-off with anything lower than what is called a region, which is a state or kind of a province or something. So that's part of the art of writing these is when to stop specifying things. So on the left-hand side, we have the R script here, and we can see that there's a fixed effects set getting created. So let's go try and find what I might have done here. And the first thing you do with the paper is you're kind of going to glance over it and see, okay, is there a table of like parameter estimates? What's going on in the paper? And, this takes a certain kind of biometric skill set. So if you're not comfortable with doing this, then this video probably isn't for you, right? So, but the thing that we're trying to spot here is something called HST, which is the height of the tree stem. And we can see that there's covariates diameter. DSOB is diameter of the stem outside bark. And so, it appears that Temesgen et al. Are fitting height diameter equations for major tree species, right? So height is the y and diameter is the x. So it looks like we have a table of parameter estimates, right? So this is when a fixed effects set would come in handy. You have like this, usually in one of these papers, you'll have a table and they'll fit a bunch of models independently for a bunch of species, for example, or maybe H classes or something like that. And they'll list out the parameter estimates, which is getting done here in Temesgen's paper. So if you go, and I'm going to go ahead and kind of cheat here, but we're going to go look at this CSV file that's stored in the models repository called HST Temesgen 2007. So this is the publication ID, and this is the model or the response variable. And you can see that we have a row here, 14.7373 for the parameter A, that matches this row, right? So this table should line up with what's in here, and it appears to. So the only difference really is that in allometric, you want to define using the family, genus, species rather than the common name, which is something that you'll have to manipulate yourself. But that's sort of the basic structure here is laid out for you. So in this CSV stored in the parameters directory, we can see that we have all the information needed for the parameters and which species go to which. So it is up to you, and honestly, like 80% of the work of allometric is encoding this information into a CSV. That's most of the work because they're in PDFs and you have to kind of convert, and it takes a lot of time, right? So, but it's not very difficult. It doesn't take a lot of brain power. So you can kind of copy them yourself one by one, or I use Excel with some sort of image detection technology to kind of speed things up, but we'll not get into the nitty-gritty there. Okay, back to the fixed effects set. So again, we're going to go through each chunk of the function call here. So the first call is called the response, and the response is the response variable, right? And it's represented by in a list with one element. And that element is named after the response variable's name, which is, in this case, HST, which is a standard code for the height of the stem, right? And if you ever want to look up what a variable means, you can do get variable def with allometric loaded, and you can see HST is here, and we would want to look at the description. Total height of the stem is what HST refers to. So there's a lot of variable names. It's honestly a separate video to go over how to come up with these, but most of the ones that you would want already are established as a thing. And if you need any help figuring those out, I'm always available. So anyway, yeah, so we have established our response variable. The next step would be to establish your covariates. So in this case, there's only one covariate, and we'll go find where table 8's models are. Let's see. So parameter estimates for base equation 4, says Temesgen. So let's go find base equation 4, which turns out to be up here. He says, here's the list of the equations, and here's equation 4, right? So it's a little bit hard to see. But you can see here that we have, okay, we have the total height of the stem, 1 plus 3 or 1.3 plus exp a plus b blah blah blah, right? Some kind of nonlinear model going on. And the important part is this d, right? This capital D represents the diameter of stem outside bark at breast height, and that's represented again by another variable name called dsob. So HST and dsob are the ones that you're going to see all the time, the total height of the stem and basically the dBH, right? It just has a special name. And we establish its units as centimeters, right? So you have to go look up and see, okay, let's make sure Temesgen's using centimeters. I'm sure he is. It appears to be a metric study of some kind, but at some point you'll want to explicitly find, okay, yeah, so we have diameter in centimeters and the height of meters. So you can see that's represented here. Okay, and then when using the fixed effect set, you need to list out the parameter names that are used. And in this case, you have, in our table here, table 8, we have A, B, and C. So you can see that lines up there. And if we go back to our parameters file, we have A, B, and C listed here. So that all lines up nicely. And then the prediction function is the function that makes the predicted height in this case. And it's just this function here, and that comes from our table 4 or table 3 function, right? So we hit this guy, and we can see everything lines up nicely. All right, so that gets you kind of started on like how to make a fixed effect set. Again, most of the work will be just converting this into a CSV, which is boring, but it is what it is. And the next thing that you're going to do is load the parameter frame. This is a special function that we'll not get into the specifics, but it's going to basically load this data set here into memory, right? So you can think of this as like a data frame loaded into memory of this data here, right? And finally, there's this other extra guy called aggregate taxa, and all that's going to do is collapse these family, genus, species columns into a taxa column, which is a special data structure that we use for species information, but not super complicated. And finally, what you do is you take your publication object that we made at the top, and you basically are going to add this set called equation 4 into the publication. And that's really all there is to it, right? So you can imagine this publication object as sort of a container, and we go ahead and make the thing that we're going to put in the container, and then we put it in the container right at the end. And that's really all there is to it. I mean, most of the work comes down to this part here, in my opinion. You have to figure out what is the response variable, what are the covariates and what units they're in, what are the parameters, what is the allometric model prediction function, and I need to load all of the parameter estimates into memory and do this other little guy. That's not super important. And once you do that, you have kind of finished a fixed effect set. So you can kind of see here, this is an interesting thing that you'll probably see a lot, is that all I did for this paper is I only did table 8, right? This equation 4 model that Temesgen's using, right? And you can see here that there's a table 9, right? There's a whole other model that I didn't even do, right? So someone is free to come along and say, okay, well, Bryce, I'm going to go ahead and add that into this file and go through the work of doing that, right? And you're free to go do that. If somebody wants to actually do that, that would be nice. So not every publication file here on the left is complete. That's totally fine. A lot of papers have a lot of models that people don't use. I'm not saying that for this paper in particular, but if somebody wanted to come by and add that later, that would be a really good exercise, I think. So let's go ahead and find what equation 14 is. So we go up here. You can see equation 14. It's listed here. It's quite long, but totally doable, right? Yeah, so you can see equation 14 just involves a lot more canopy competition factor, I believe is what that is, and basal area of the stand. It looks like for me, all I was doing, I was just adding a model that only uses the diameter, right? So anyway, fun exercise if you wanted to go add that. Would be a good low-hanging fruit for somebody. All right, so that gives you a flavor of how a fixed effects set works. And we'll go ahead and look at a fixed effects model next. Okay, so if you thought a fixed effects set was confusing, which I don't think it's too bad, you'll find the fixed effects model class even easier to understand. So I'm going to come in a little cold on this, and I think that's kind of nice because you'll see me sort of live interpret my previous work here. We're going to take a look at fixed effects model, right? So we can see here in this publication file called Harrington 1986 that we're using a fixed effects model. And it looks very similar to the fixed effects set before, right? We have a response, we have the covariates, we have the parameters, we have the prediction function, right? The only thing we don't have in this case is the model specifications argument, right? We don't need it, and we'll kind of see why that's the case. So again, we start with our publication file or publication object on top. It has a citation, which is listed here, and that should match on the right-hand side, right? So we have height, growth, and site index curves for Red Alder by Constance Harrington and Bob Curtis. A nice legacy publication from 1986 about a very interesting topic, Red Alder productivity. So that, that's kind of a fun thing about doing this. If you're kind of a biometrics geek like myself, it's fun to, look at all these publications that, some of them, I'm sure this model is used probably in FES or something along those lines, but it's just nice to kind of like look at all this stuff. I mean, look at this great art, this line art of a nice little alder branch. It's just fun to do. So I get a kick out of it. Hopefully we can find a few other people that also like it. So anyway, again, we have our publication descriptors. We're operating in the US. In this case, we have US, state of Oregon and Washington. So we kind of want to verify that that's the case if you're writing this first. And in this case, we can see we're declaring a taxa object, which contains one taxon in this case for Red Alder Betulaceae alnus rubra. And yeah, let's just keep going down the script here. So we're fitting something called HSTIX20, which is a fixed effects model. And HSTIX refers to site index. So site index, I think most of the time, refers to the height of a tree at a base age. So in this case, the height of the trees, or the base age is 20, right? And typically these models take the structure of HSTIX as the response variable, in this case feet, and then usually you just have two covariates, which is the height of the tree and the age. We'll not get into that stuff in particular, but at the end of the day, it's a kind of allometric model in a sense. And allometric is totally capable of handling site index functions of this kind. So anyway, let's proceed. At some, just looking at this, with the trained eye here, we can tell that we're fitting a fixed effects model, and it has these parameters, and that might be all the paper does. There might be more to it. Let's go find out. So again, just kind of scroll through. Eventually you get pretty good at sort of sifting through all this stuff pretty quickly. And in my case, I haven't seen this one in a little bit, but it looks like here we have let's just take a look at our prediction function as a plus b times HST, and look where we have that, right? So we have a plus b times height in this case. So you can see the similarity between those there. And it looks like we have our parameters listed here, 16.518, you can see that one here, and 1.407, or minus 1.407, so on and so forth. So you can see some kind of coherence between the paper and what's listed here, right? So it appears that that's the model that we have written up here in allometric. And it's pretty straightforward, what I would point out is, you have your prediction function block, and then you have your prediction function here at the end. And at some point, I probably just had to name these parameters A1 through A4, right? And if you can see what Connie's doing in this paper, she has a parameter. A is kind of written as like a sort of separate piece here. And that's fine. So I probably just ended up naming this one A1, A2, A3, A4. And then you have B1, B2, B3. So that was probably something that I came up with. And you're going to have to be comfortable doing that, right? Not everything is going to be completely laid out for you in this case. But that appears to be the only creative part of this this script here. So pretty straightforward. And again, we create our publication object. We create the thing that's going to go inside. Sometimes there's more than one of these. We're just kind of focusing on simpler papers for now. And you go ahead and add the model in this case to the publication object, and there you go. That's pretty much it. So the interesting thing that I'm wondering is, did I fit everything in the paper? Are there other models that we could have added and didn't? It looks like mostly discussion here. Yeah, I'd have to dig a little bit more and verify, but it seems like we have some other guy going here. Equation 4 is fitted. Yeah, it could be interesting to go back and see if there are any models to pick up back in this publication and add them into the script. So that could be something a motivated person could do. But typically when I add a publication, I try to go for, I'm trying to add a lot of stuff, and I don't want to spend my time on sort of secondary results, I guess you would say. And in this case, the obvious thing that people typically want from this publication is the site index curve, but maybe you want the height growth curve as well. In that case, we would need to add it. So there's always things like that to find. But in this case, the difference between FixedEffectsModel and FixedEffectsSet is, again, we just list the parameters out, and there's only one model that is in the paper or in the that we're adding at a time. So there you go.